Hi there, everybody. So we are into Module 2, and I hope you're having a good time. I will be giving you more feedback a little bit more timely in this module, so please keep an eye out for that. But first I want to talk a little bit about induction. And I figured out finally, so you can see my face while we're talking through this. So you should see my whiteboard there. And basically, I've mentioned this to a few of you, and you came across one of the problems on the diagnostic test was actually an induction problem. And it was just to see who had seen that before. So for those of you that haven't seen it, I had told you when we talked that we would get to it, and here we are. Basically, mathematical induction is based on looking for patterns among the natural numbers. And you may already know that the natural numbers, another name for them, are the counting numbers. So 1, 2, 3, 4, 5, so on. Sometimes we don't start at 1 in these problems, but generally speaking, we're looking at positive integers. And the fact that one integer follows another, there's no, this is not a continuous set of numbers. There is spaces in between, and so we need that pattern in order to establish the induction proof. So I'm going to use this example. It's on page 51 in the book, number 10. Hopefully you've read about this ahead of time before watching the video. And feel free to stop the video at any time and kind of think about what I'm doing, back it up, go over it again, whatever you need to do in order to understand this. Okay, so we're going to look at this problem right here. So basically what we're looking at is the left-hand side is the sum of all the natural numbers, and we're saying that that should equal the nth number times the n plus 1 number and divide that by 2. Some of you may be familiar with an apocryphal story about a mathematician called Carl Friedrich Gauss, and there was this story that supposedly his teacher was kind of tired of his precociousness and sent him off to his desk to add up all the numbers 1 through 100, thinking that it would take Carl a long time to do this. And again, the story goes that Carl actually figured out this particular formula and walked back up very shortly to his teacher and said, here's the answer. So whether or not that's a true story, it's an interesting one. And as a personal note, we actually had 2 of his descendants at my school that I work at now. I had both of them as my advisees, so it's kind of fun to see those connections. At any rate, so let's take a look at this. The way that mathematical induction is set up is we start with what's known as the base case. So usually what we'll do is we'll start with the lowest number that we're looking for. So in this case, we're starting with 1. Sometimes the problem will say n is greater than some 3, 15, whatever. The example in the diagnostic test said n is greater than 7, so we'd start with that. But in this case, we'll start with 1. So I'm going to write this down as my base case. And I'm going to say let n equal 1. Okay? So then we're just going to go ahead and we're actually going to think about that. What would the left-hand side look like? Well, since we're counting up all of the numbers to 1, we basically just have 1 on the left-hand side. And then on the right-hand side, I'm put a little question mark there for a minute over the equals, we would have 1 times 1 plus 1 over 2. And then we do the math. We figure it out. Like, is that really a true statement? So if I add the numbers, I get 1 times 2 over 2, and then clearly 2 over 2 is 1. So what we've done is we've shown this is true for the value n equals 1. Okay, for an induction step or an induction proof to work, we have to start somewhere. Okay, and then comes the inductive step, and what the inductive step does is, and I should actually, going back up really quickly to this one, this is the same thing as saying p of 1. Okay, and so what the inductive step says is that if p of k is true, this should imply that p of k plus 1 is true. Okay, and here's where the natural number piece comes in. It's because if I know it's true for one number and I add 1, and I can show it's true for the next number, then I've got it for that one, and then it's true for the next one after that, and so on. So what this is saying right now is, if my k is 1, which we've shown is true, and I can show that it's true for k plus 1, then essentially what I'm doing is saying that it's true for 2. But then that means it's true for 3, and it's true for 4, and so on and so forth. Okay? So what we do with the inductive step is we start by assuming that P of k is true. This is another way of saying let n equal k. So what does this mean? It means that, in other words, 1 plus 2 plus 3 plus ... plus k equals k times k plus 1 over 2. And you might be sitting there going, well, wait a second, isn't that what we're trying to prove? And how can we just go ahead and assume that's true? All we're doing is saying that there is some k out there for that this is true. And since our base case actually proved it for us, that we showed a number k that works, we know there is some k out there is true. Okay? But what we want to do then is the next step is now we show that P of k plus 1 is true, or n equals k plus 1. So what we need to do is we need to somehow figure out what this would look like. So off to the side here, I'm just going to move this over for a minute. Off to the side, just for a second, I'm going to say, oh, P of k plus 1, what would that look like? Well, on the left-hand side, that would be 1 plus 2 plus 3, ... k plus 1 equals, and on the right-hand side, we'd replace n with k plus 1, and k plus, and in both cases, so k plus 1 over 2, and so the right-hand side ends up being k plus 1 times k plus 2 over 2. Okay, so this is helpful to kind of keep in mind. That's what we're trying to aim for, but we can't start with that one. We have to get there. So I'm going to start with the statement we know is true for some k. So we're going to begin with 1 plus 2 plus 3 up through k is equal to k times k plus 1 over 2. Because again, we know this is true for some k. We've already shown that there's a k out there. But what I'm going to do now is to make the left-hand side what I want, which is this thing over here, I'm going to just add k plus 1 to that. But equation solving, whatever I do to one side, I do to the other. So I'm going to add k plus 1 to the right-hand side as well. So I haven't changed anything. I've just added a term to both sides. Now the left-hand side is what I want it to be. So the right-hand side, well, I'm going to add fractions. So I'm going to find a common denominator. So the second number, if I multiply by 2 over 2, and I'll get k times k plus 1 plus 2 times k plus 1 all over 2. And now you may notice that I have k plus 1 in both of those places. Okay, so I'm just going to back out so it's not quite as messy. But so I'm going to factor out k plus 1. Oops, let's change that to black again. So I factor out a k plus 1, and what am I left with? I've got k plus 2, so k plus 2 all over 2. But that's what we needed to show. So therefore, P of k plus 1 is true. And we have proven our statement. So that's it. That's induction, proof by induction. Doesn't work if we're not working with natural numbers. Real numbers can't work because there's no pattern of here's a number and then we add 1 to get to the next number. Got to be natural numbers. But yeah, that's how it works. Hopefully that made sense. Again, feel free to review it. Feel free to ask questions if you have them. And we will take a look at some more practice of this going on. Thanks.